Today's topic is bats and wind. And we're talking about both of these things because they are both really valuable parts of our environment and environmental future, where wind energy is a wonderful, cheap, renewable source of energy, and bats are great for ecosystems, and we want these two things to be able to coexist, and there's a concern that they may not be. So we want to look into that and try and figure out what we can do about it. The first step is for me to convince you that wind energy is awesome. It is basically the cheapest electricity source around. It involves relatively minimal environmental impacts. You can use cropland, you can use land that's otherwise uninteresting, put up windmills there and have a relatively low environmental impact in the grand scheme of things. And check out this cost here. Way cheaper than natural gas, nuclear, all of these other options are available to us, but wind is one of the most reliably cheap options there, with solar coming in pretty close after that, but these two things can go together very nicely. So we want wind energy to be around, and we know that the wind is not always blowing, but it's great when it does, and it blows a lot. So here is just a snapshot of time from the UK and the UK's energy grid, looking at how much energy they were getting. This blue area here is wind, that was electricity generated by wind, and all these are the other sources that they were getting. And so they have had a huge amount of wind during certain times of year. They can get a good portion of their electricity needs. And, we said the wind is not always blowing, but actually on average, a wind turbine has a capacity factor. That's about, out of its total possible peak energy output, if it had its peak all the time, what percentage of that is it actually producing? And most wind turbines have an average of about 42% of their capacity factor. So they're generating electricity a little less than half the time. But that's a really valuable, cheap source of energy, even with that lower capacity factor than, say, nuclear, which is always on, which is this green bar here that just, it's steady, it's reliable, it's constant, and that's great. But it has some other drawbacks, and so what can we do to make wind work a little bit better? And just to give you a sense of how valuable wind is to different places, 60% of the electricity in Iowa, almost that much in Denmark. The UK is down about 30%. Texas, we don't normally think of as the lefty green renewable energy capital, but in fact they get 30% of their energy from wind over the course of a year, which is more than Germany and way more than lefty California there, which gets about 10%, which is pretty typical for the US average and a little bit higher than the world average of around 8% of the electricity mix coming from wind. So wind is super valuable in many parts of the world and becoming more valuable, especially as we start pushing wind more offshore. So you'll hear more about that in other places, but just know that wind is valuable. So I've got a picture here of the tallest building on the CSUN campus. It's 7 stories tall, and I wanted to see if we had one of these modern wind turbines on our campus. What would it look like? How tall would it be? Would it go up to the 3rd floor? Would it go up to the top? Would it be taller? Well, let's go ahead and just place one in here. Oh, well, I think we need to zoom out a little bit. Oh my goodness. These modern wind turbines are very tall, like 3 times taller than Sierra Tower, the tallest building on our campus, and they sweep out a huge area, like probably more than twice as big as the entire building face of the Sierra Tower complex here. So this is something that is very large. And what that means is that as the wind pushes those huge blades, it can generate a lot of electricity, like 2 to 3 megawatts of electricity, which is, when it's turning, produces enough energy in 45 minutes to power a home for a month. Or basically over the course of a year, you can have 1,000 homes generated by one wind turbine. So lots of energy potential from these things. They're super valuable, but they are kind of big. And let's just get a sense for how fast those blades are moving. They don't look like they're moving too fast, but let me go ahead and just have this little video spin around here. And these blades, they can be 50 meters long. And so how quickly does it take for one rotation to happen there? Each rotation is producing enough energy to power a home for about an hour. So lots of there, but when we think about the outer edge of this blade here, how fast is it going in miles an hour? Well, if you pause it and you know that this takes about somewhere between 2 and 3 seconds to go around in a circle, and it's sweeping out the entire circumference on the outer edge. So that's pi times d, that's 100 times 3.14, that's 314 meters in a couple of seconds. That's more than 100 meters per second. It's up, that works out to be more than 200 miles an hour. So we're talking about extraordinarily fast moving blades. And so if you think about being a flying animal in this context here, it could be very scary. There's collisions with unanticipated moving objects. So even though the windmills look like they're moving kind of slow to our eyes, they're actually sweeping around, especially at the outer edge, at way faster than, say, a semi-truck, and they are way bigger than a semi-truck. If you look at them, they're more than twice as big as trucks. They move more than twice as fast. And so these are things that are hard to anticipate the motion of for a small critter, which is why they can get struck by these windmills. And in fact, the blades here's some pictures. These are a lot of slides in here, and a lot of the knowledge from here comes from Joe Shusak. You can see a picture of a bat colliding with a turbine blade. In this picture, you can see it in thermal infrared here, and we end up with bats and birds both at the bottom of windmills dead. And we have a question of how often is this happening? Is this a real problem or just a little occasional thing that happens? And so how would we figure this out? Well, we'd go out and we'd search. And of course, many wind farms look like the areas like this with very tall grass. So this idea of let's just look for the carcasses is a little bit harder than it sounds. And you have to have a very detailed strategy for doing this. And when you finally find a bat, it might look something like this there, kind of hidden halfway underneath the grass. And so it's very challenging. The predators, not predators, scavengers will carry these things off or consume them to make them even harder to find. So you have to go out there pretty often before the scavengers get there. And it's a very time-intensive thing. It maybe could help. And in fact, some folks have done some research on using dogs to help locate carcasses so they can really get a good measure of how many bats are actually dying. And here is an example of one research study, not from a single windmill. This is a little bit of a misleading figure here. This is showing a compilation of 20 different wind turbines over 40 days and all of the bats and birds that died off. And there are apparently 466 dots on this map here, which works out to be, during this peak time period, almost a bat a day on each of these wind turbines. Now, this is not, we'll see later, this is not happening year-round for every wind turbine, but at this peak time period that they had, there were a lot of bats died, and you had to search over a very large area to find all of them. Well, let's take a look at what happens when you do. You have those bats in your hands, you can now identify them. And so we can try and get a sense of what things look like. So here is from one wind farm in Texas looking at the types of bats that were killed. And there are more than 20 different types of bats in Texas. And so we don't see 20 different little bars here representing different types of bats. We only see just a handful of them. And in fact, the most of the bats that were collected are this eastern red bat. You did see some of these Mexican free-tail bats collected, and you might remember the Mexican free-tail bats are the bat that lives in Bracken Cave. There are more bats in Bracken Cave than there are people in Texas, and so you've got more than 20 million of those bats, and yet they make up a very small fraction of the bats that were killed. Red bats are probably many fewer in Texas, and yet they are killed at a much higher rate. We also have this hoary bat killed off. There's the silver-haired, a couple other bats in smaller quantities, and a few that were unidentifiable. So is this one wind farm? Is this an exceptional thing that maybe this wind farm is located right near where those eastern red bats happen to be? Is this something that's a trend that we should see? Well, here's a different study actually a different paper that compiled a bunch of other studies from different wind farms all across, from Canada down to the south central United States. Each one of these is an individual wind farm, and these are the different species of bats that were collected at each of these, including others. So almost all of them fell into 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of the 45 different bat species that we have in North America or in the United States. So we are seeing only a small fraction of them. And let's see, I color-coded here for ones where more than half of the bats that were found were for one species. So you can take a quick sense there. And then there are a few of them that are more than a third of the bats that were found at that wind farm are of another species. And I'm hoping you're starting to see a trend that this one type of bat, the hoary bat, seems to be really strongly impacted by wind farms. And here's our eastern red bat that we saw in that one example before. It seems to also be affected. And we see some silver-haired bats in some cases, occasionally those free-tailed bats, but a lot of others are really not very commonly killed. They're just occasional ones. We're really seeing just a few types of bats. So even in the last column here, we have this column which shows what percentage of the bats that actually live in that area were discovered. So in this case, they have only a third of the different types of species that live in that area were actually discovered. Down here at this place in Oregon, they had only 13%. So that's like 1 out of 7 of the species that they had in that area were actually discovered. And the other 6/7 of them did not actually get killed by the wind farm. So what are we to make of this pattern? Let's take a look at a little bit about these here in compilation. This is the percent of all of those together here, and you can see our hoary bat is the biggest affected type of bat. And this is not a very comprehensive or completely accurate table, but it shows here I've divided up the bats into 2 different categories of largely migratory and largely hibernating without much migration, without much large-scale migration. And then kind of where they're popularly roosting. We have bats that are in green are the ones that are primarily tree-dwelling bats. The red ones here are primarily crevice dwellers, the gray ones are primarily cave dwellers, and then the other ones on this list here are kind of, they have more varied roosting preferences, and so it's not quite fair to put them in one category or another here. And so let's take a look, if we look at the numbers, what sort of things are we noticing about this? Which types of bats are the ones that are most affected by the windmills? Well, you can see that almost all the bats that are killed here are considered the ones that are strongly in the migratory category. And then among those, the ones that have the biggest impact of all are the ones that are tree bats. And so migratory tree bats seem to be most strongly impacted. And let's try and unpack a little bit about why that might be. Well, let's start with the migratory part. Well, this is a graph showing at what height in the air column do a lot of bats fly when they're flying past a wind farm. And this doesn't go, there are additional bats above this, but where are we seeing bats? Very few of the migratory bats are flying right down near the ground surface. And as you go up higher, more and more bats and birds fly up higher, which is a problem, of course, because these windmills are getting taller and taller. And so as we get windmills intruding higher into the air column, they're intruding into more of the flight path of more birds and bats. And so they're more likely to end up killing more of them as they fly past. So migration is definitely a part of this story here. And we're seeing that these taller windmills are going to have more of an impact on the bats than say a shorter windmill, like some of these more younger windmills and some of the older windmills, the ones that were created earlier on, are much shorter than today's modern windmills, and so they don't have nearly as much of an impact on bats and birds as these tall ones do. But let's take a look at this idea of the tree part. We got the migratory part, but let's take a look at the tree part. And this is a great figure from Joe Shusak, just sort of illustrating here what it might look like here. Which of these is a wind turbine and which of them is a tree snag? And of course, it's a joke. You can, as a human, you could probably pretty easily tell there. But maybe these turbine silhouettes might look kind of similar to a bat's search image for what a roost looks like. And we really can see a little bit of evidence from that in this next graph here, showing not the species, but the gender of the bats that are killed. And I've colored here, blue bats are male and kind of pink bats are female. Sorry for the color coding here, and then juvenile are a little bit lighter colored, and the adults are darker. And with the exception of this one example from Tennessee, the other ones that we have here, if we ask the question, which are more likely to die, male or female, you can see that there's a strong preference towards male bats dying off. And so we have to kind of wonder, why might that be? And there's a couple different possibilities, including different behaviors to how those bats will interact with roosts. A lot of male bats like to be territorial. They like to go and they see a new roost option. They want to go over there and just check it out and maybe stake their claim there. And so it's possible that we're seeing that state claim staking or some sort of reason why the males are more likely to go over there than females are. That's entirely speculative at this point, but it is important to note there is definitely a difference, and it might be a clue as to why the bats are going over towards those windmills and why they're getting killed by them more likely. So definitely we are seeing an impact here on birds and bats from these wind turbines. And I do want to, though, put this a little bit into perspective here when we think about all the different things that are killing birds in the United States that from related to humans. And the number one killer here is our pets. Way more way more birds die from cats than collisions with wind turbines. And we have electrocutions from landing on electrical lines. We have poisons from our different toxic things that we put out there, collisions with vehicles, collisions with big tall buildings. Just like wind turbines, buildings are very tall. They can end up messing up the flight path. And so this is true this is a graph for birds from the Fish and Wildlife Service. I don't know if a comparable set of data exists for bats, but we can presume that there are other anthropogenic things that are killing bats more than just wind turbines. So we do want to keep that in perspective. And with that said, it would be nice to eliminate any deaths that we do have from these wind turbines. So what could we possibly do? Knowing that this is not the biggest problem, but it is a problem, is there a solution to this problem? Well, what can we do to help bats? Some research has been done to help us look at this. And so here's a heading from a newspaper article, actually. Red light spells danger for bats near wind turbines. And if you don't know, a lot of wind turbines have these little red lights that blink on top of them. And if you're driving past at night, you might see something like the scene that you're seeing here with these lights turning on and then turning off. And these are aviation lights that look something like this. And so this research study described in this article here, researchers installed a pole, they put some lights on top and looked to see, does this attract the bats? Does it, if we turn off the lights, would we have fewer bats? And this study, you can see from the headline, found that these lights were really important in attracting bats to wind turbines. But it's not a very compelling study. They took a 24-foot pole and lit it up with some lights that were different colors. And is a 24-foot pole a good model for what a wind turbine looks like? Definitely not. We saw how tall they are, 3 times taller than Sierra Tower. These are huge things, and so this may not be a great study. So what we can actually do is we can actually look at a more detailed study that took those blinking lights and went out and looked at those carcass searches, those systematic carcass searches to see where are bats dying. Are they dying near the wind turbines that have lights or the ones without? And from this little picture here showing the average number of bat fatalities per search, they're seeing that when the lights were on, they tended to actually have fewer fatalities. And it does seem to be statistically significant here. So the idea that the bats are attracted to the lights is not holding to bear in terms of them getting killed by them. In fact, maybe even there's the tantalizing evidence that having those lights might actually reduce the fatalities, perhaps because maybe they look less like tree snags. I don't know exactly why this is true, but definitely not true that having the lights on is going to attract the bats and cause them to die more often. So that's not going to solve it, I don't think. Next up, maybe there's something about the sound. Are they attracted to the sound of the blades? Is it interfering with their echolocation? And so this is a slide also from Joe Susak, was showing the whoosh, whoosh of a wind turbine sound here, and seeing the sonogram of it. And what you're noticing here is this red line is kind of the boundary between human hearing and where most bat calls are, and where are you seeing the sound of the wind turbines. I can show you that in another picture here, showing the ambient noise versus at the base of a wind turbine in a spectral power density here, and we're seeing most of the energy is happening at sounds that we can hear, sounds that bats maybe can hear, but doesn't really annoy them in general, and is not terribly different when you get into the sounds of echolocation. The noise intensity is not going to interfere with their echolocation, and not really a big difference there. So it doesn't seem like it's the extra lights of the windmills. It doesn't seem like it's the extra sound from the windmills. So what are we going to figure out here? Well, let's talk more sound. Maybe there's no sounds that are annoying that annoy bats now, but could we make it really loud and annoying so bats would avoid a wind farm? And there are these great speakers that exist. They're ultrasonic broadcast units. They make very loud sounds. You can play back recordings of different scary things that are scary to bats. You can play back loud noises to them and see if you can drive them away. And will this work? So the first step to doing this before we go approach a wind farm and try and convince them to buy a bunch of these things is to test this out. So let's start small. Let's just test it out in a laboratory and see if we can scare bats away. And so the first studies were done in little test rooms where you release a bat to fly, and they've divided this room into 4 different quadrants and put a speaker in one of the quadrants. And sometimes they put in little mealworms there around, and they're playing static noise that ranges in the ultrasound there, really loud. And they're trying to figure out, do the bats avoid the quadrant with the speaker? So what do you think? Think it's going to work? Let's take a look at some of their results. So here we have the control, which is the situation where that speaker is there, but it's not making any noise. And then the speaker where it is on is the experimental case. And you can see that we've cut down the flybys through that quadrant quite a bit. We've cut them down to a third of their original value. So we're definitely scaring or annoying the bat away from that. And it turns out that it doesn't matter whether you put food there. Even if you put food there and they're like, ooh, I see the food, they still don't go there because it's too annoying. And in fact, when they did go there to get the food, they were unsuccessful in catching those mealworms. And so they probably wouldn't go there very many times when they realized that their echolocation was really interfered with by the sound. So it seems to be working. All right, let's try scaling this up a little bit. Let's go outside and let's see if we can do this out in nature. Will this still work when we go there? Because I still want to provide this wind farm a really detailed study that shows this is going to be a great idea for them. And so let's choose a place that bats like to go to, like a pond. And it has to be a place where there's a lot of activity there, that we can really concentrate a speaker and scare. It's concentrated enough that we can scare away the bats with enough sound or annoy them away, but large enough that they can fly away and go find another spot, basically. So we want to avoid the idea of them having to come to this spot because it's the only water around for miles, and so let's see what happens. And we've done this here, or not we, but folks have done this in this research study at a whole bunch of different places around the western US, and to see if they get the same results. And here are those results. Did it work? You're seeing before the treatment, before they turned on the speaker, what the typical activity levels were on those different days, and then they turn on the speaker, and seeing what happens to the activity level. 90% reduction within 15 meters of the device. And more importantly, it's a sustained effect after several days. They don't just get habituated to it. They keep away from it because it still annoys them after days of this. And that seems very promising. So I think we're ready to go visit a wind farm and tell them about this great idea, shall we? Well, they did indeed get a wind farm to give this a try. They put not just one of these things on there, but a whole bunch of them on both sides of a wind turbine's tower, and it got way up there. Blasted this music, or not music, it was loud ambient or random noise here. Did it work? The first 10 days they were there, they put the speakers on turbine 275, and then turbine 212 was kind of nearby, and they set up a monitoring system right near that. They had infrared cameras, they were monitoring for night after night, looking at how many bats there were, and there were different numbers of bat passes on each night, which is why you have these box plots. But overall, there were fewer nights with lots of bats on the experimental site, the one with the sound, and it seemed to be working. They're like, oh my gosh, this is pretty exciting. But then they moved the speakers to another tower, turbine 296, and then their nearby control to that one, the kind of the equivalent tower nearby, was number 240, and they did it for another series of days, another 10 days. And here, the results were not quite as promising. Here there were more days with bats, with lots of high numbers of bats at the sound site, the one with the annoying noises. There were more bats coming nearby that one. And so, gosh, our two experiments produced contradictory results. And so it's possible that there is actually an effect, but it's also possible that it's not true. In fact, the statistics tell us that at least 3% of the time that we do this experiment, we should get the opposite happening according to the statistics here. So this could be by random chance that we're seeing this, and it's certainly not a super compelling result where it happens and helps and works every time. And so why not? Well, the first thing that we should remember about why it doesn't work is that ultrasound attenuates really fast. You've got to be really close to that speaker in order for you to hear it loud enough for it to be annoying. And so, that's even though they had 4 different microphones on there, it wasn't a lot of microphones, and they don't travel for very far, even though they were as loud as they could make them. Even if they did work, let's see some problems with this. Well, the study says, in our study, the acoustic envelope of the deterrence was far smaller than the total volume of air occupied by the turbine. And so they'd have to have way more of these microphones, and it's going to get more expensive and more complicated to run. And you run out of tower. The top part of the turbine, which is where higher altitudes are more dangerous for the bats. There's no tower to put things on up there, so you'd have to start putting things on the blades. Can you even do that? So we're starting to get some problems with it. And then, even if it does annoy the bats, this says here that bats flying into a large acoustic field may be disoriented by the emissions. And because this is such a broad area over which the sound is there, they're not able to turn a tiny little bit and avoid it. So if they turn a tiny bit and it's just as loud, turn it a little bit the other way, it's just as loud, and they're like, oh my gosh, well, there's no way I can avoid this. What's the best pathway for it to go? Unfortunately, straight ahead. So if it's disoriented, if it can't avoid it, it's just going to keep going on the path it was doing before. And so this is not necessarily a promising technology for us. It did work a little bit at reducing bats in one case, but it's not necessarily going to work as we try and scale this up everywhere. And there's a lot of reasons to think that it may not work even at all. Okay, so we need something new. Let's take a look at some other data. So we've looked at carcass searches, and those carcass searches have been done day after day after day. This is an example of a very detailed study that went from April through November, looking at the timing of when carcasses were collected, and you can see that it's not all the time that we have really high numbers of fatalities. In fact, there's really only a very short period of the year where there's a lot of fatalities. And you might know, of course, that when putting together what we learned before, that's the period of migration. And this was from 2009. If we look in 2010, you can see that same general pattern at that same site. Relatively few fatalities for most of the year, and then this peak migration period where we have more fatalities. So interesting. It's only a short period of time, so you could argue, well, maybe we could convince wind turbine owners to turn off their wind turbines during this month-long part of the year. Well, if you're a wind turbine owner, and I just told you, please turn off your wind turbine for 1/12 of the year, and your profits are going to go down 1/12. In fact, actually, probably more than that, because this is some peak wind season, some peak electricity usage season here. I'm not going to do that. Can you come up with something better for me? Something that's not going to cost me as much than 1/12 of my time. And so we got to look a little bit harder here. And so we got to figure out, let me go back actually here. There's certainly a lot of variation even between one day to the next here that could be related to migration, or it could be related to some other factors. So what are some of those other factors that might be affecting the number of fatalities between, say, this day right here and the next day where it was much lower and the day before, which was much lower? And you might say things about temperature, or let's look at wind speed. Now, here's a histogram showing the wind speeds of percent of days on different that had different amounts of wind. And you can see there's the few ones that are really high, a few that are lower, and most of them are kind of in the middle range. And so, do you expect more fatalities on days with high wind or days with low wind? And think about this. There's reason for both sides of this. You might say on a day with high wind, the turbine's going to be turning really fast, and so we'd expect more fatalities. Or you might say on a day with low wind, there's going to be more bats out there, and so there's going to be more fatalities because there's just more bat activity. So we've got an argument for both, so let's take a look at what do the data show. This is a plot showing wind speed at two different wind facilities here with number of fatalities, and it's not a perfect correlation, it's not a perfect straight line, but you can see that in general, days with lower wind speeds seem to be the ones with more fatalities, and that's probably because of there's simply more bat activity at these altitudes where we have the windmills. So. Well, maybe we could just turn the windmills off then when there's lower wind activity. That's when windmills aren't even producing as much energy anyway. So this is going to be much more promising for our selling it to our wind farm owners. And so let's do a trial of this. What would happen if we turned off wind turbines in low wind? And so this is actually not a terrible thing, because actually most windmills don't even actually turn on unless the wind speeds get above about 3.5 meters per second. That's called the cut-in speed, and there's simply not enough energy to turn those huge blades when you have really low wind speed. So there's a cut-in speed. This is actually just all we're asking a wind farm owner to do is to change the cut-in speed. So right now, if they are more than 3.5 meters per second, those blades turn on and start rotating, or not turn on, but they unlock and they start rotating, and so they generate electricity. What if we change that to 5 meters per second? So we kept the wind turbine locked and off for lower speeds, but then allowed them to start spinning when there was more energy, or even more conservative, more safe if we kept them stopped for up until 6.5 meters per second. You can kind of see on these graphs where those are, 6.5 meters per second and 5 meters per second. Those seem to be kind of led by the data to avoid those highest speeds. So let's go ahead and see what happens with these trials. What they've done is turbine by turbine here. They've looked at different cases where they turned them on for, say, 10 days at a time with their usual setup, with the cut-in speed that's a little bit faster, the cut-in speed that's a little slower, and tried out these different options here, and they rotated through the different turbines so they could, weren't doing all this the different times in the migration. And what are you seeing in this graph is that the business as usual 3.5 meters per second cut-in is when most of the fatalities were happening. And then the blue and green options here, not as many fatalities there, and not a huge difference. And if you sort of add all those up here to a total number of fatalities, you get somewhere around 4 fatalities during the study period, plus or minus 2 when you're at the low cut-in speed. And you have about a 75% reduction for both the 5 meters per second and 6.5 meters per second, and no statistical difference between those other cut-in speeds. So we now have a suggestion for our wind farm owners. Could you turn off your wind farm when the wind speeds are low and during the migration period only. So we're looking at a very small time period where we say, please turn off your wind turbines. And how much is this going to cost you? Well, if you take a look at this for the 5 meters per second cut in and over that short migration time period where we want to turn off the blades, it's only 0.3% less annual output. And if you are more conservative and you go up to that 1% annual output cut for the 6.5 meter per second cut-in speed. So this is not a huge ask of a wind turbine wind farm owner. They want to be good stewards. They want to play a good part. They want they're choosing to make money using an environmentally friendly electricity method. These are the type of people where if we tell them, would you be willing to spend 0.3% less to kill lots fewer bats that are important for the ecosystem, this is actually a relatively easy sell, and maybe we can even find some compensation for them. So this is very promising, and this has been proposed to a lot of turbine farm owners, and so we have the chance to make a difference here because of our studies of bat activity. So some quick conclusions from our day today here. Wind turbines are awesome. Blades turn really fast. They're hard to avoid. That's why bats die. In particular, migratory bats are the ones that are dying the most often. It turns out that acoustic deterrents are probably, they sound like they'd be cool, but they're probably impractical and won't work very well. So the best way to save bats from the blades of wind turbines is curtailment, turning them off at low wind during critical migration months, and that can reduce bat fatalities. So I hope I've convinced you that bats and wind can safely and successfully coexist, and that we can make our studies of science help make that symbiosis even more effective.